All right, what we're going to talk about today is the divergence theorem. This is section 16.9 in the textbook. And this is, like we said in class, this is the flat case of the three-dimensional, basically fundamental theorem of calculus, like we mentioned in class. It's going to be built off the idea we need this notion of a simple solid region, which is a three-dimensional region that's of type 1, 2, and 3, like we defined in the section 15.6, which was on triple integrals. So basically, a simple solid region is a three-dimensional space, three-dimensional shape that can be integrated in any order. So you can do dx, dy, dz, dy, dx, dz, whatever you want. Okay. If you start with that, then what you get here is the divergence theorem. So you start with a simple solid region E, and S is the outside of the shape. Sometimes we'll call this the boundary of the surface, the boundary surface of E. It's the positive orientation, which is just the outward orientation. So like we mentioned in class, if you have an enclosed shape, you can have an outward normal for the orientation of the surface or an inward normal for the orientation of the surface. In this case, we'll call the positive orientation the outward normal for that shape. If f is a vector field whose component functions are nice, meaning they have continuous partial derivatives on some open region around E, so everything's big enough and nice enough, then you get this really cool theorem that says that the surface integral of f along the boundary, so this is the flux integral, remember that, is actually equal to the triple integral of the divergence of that vector field with respect to the volume element in the space. This is a pretty nifty theorem. Again, look at the how it compares to Stokes' theorem or the fundamental theorem of line integrals and Green's theorem. You have a derivative object with a higher order integral, and you go up one level in antiderivative, up one level in derivatives to get this object here, and down one dimension in integral. So all of the different fundamental theorems of calculus seem to have this feature. Okay. Really, what's nice about this one is that it's one of the easiest ones of the things we've done in this section to actually apply. And so for the rest of this section, we're just going to do an example where we'll verify that this actually holds for a particular case. So here's an exercise here. We're going to verify that the divergence theorem holds for this vector field here, where E is the solid enclosed by the paraboloid z equals x squared plus y squared and the plane z equals 9. So that is this surface right here. Let me zoom out just a tad. Okay, that's this surface right here. So you can see here's the z equals 9 plane, that's the top part, and then here's the paraboloid. So this is the surface z equals x squared plus y squared. And so what we want to do with this surface here is we want to take this vector field and verify this equation right here. So we're going to compute the surface integral of the boundary and show that that's the same as the triple integral of the divergence on the inside. All right, so we'll do the surface integral first. Now if you look, we have a bit of a challenge here because we actually have two pieces to the surface. We have the top part of the surface and then the bottom piece here. I know it's two pieces because those are the smooth parts. There's a corner right around this boundary, so I have to break up across that corner. This is the idea of being piecewise smooth that we mentioned before. So we're going to do each of these pieces. We'll do the top part here, which I'll call S1, and we'll do the bottom part here, which we'll call S2, and the entire surface around it is S. So we'll compute the surface integral of the top, the surface integral of the outside, and then add the two together to get the total surface integral. Now if you look, we want the outward normal direction, so just before we get started, let's take a look at where the direction should be pointed so we know which normal vectors to pick. On the top, if we want the outward normal, this is going to be the normal that's going to be pointing up in the z direction. But down on the bowl part, even though it's kind of small, the normal vector everywhere on this edge here points a little bit down. A lot down when you get down to here, but a little bit down up here. Nonetheless, the outside normal vector is going to be a downward normal because it's going to have a negative z component because it'll be pointing slightly down. So the top one's going to be pointing up, the sides is going to be pointing down when we look at the normal vectors. All right, so let's do this piece by piece. Let's look at the top surface and go from there. So here's the surface integral. The top surface, S1, is this top plane right here, which is z equals 9. And if you look, we just have the x and the y are in the circle of radius. Well, we have to know what z is. Z on the surface is equal to x squared plus y squared. So z is the radius of the circle. So if we have, sorry, z is not the radius of the circle. Z is the square of the radius of the circle. Okay, if you look here, we got x squared plus y squared equals z. Z is going to be the square of the radius of the circle. So if z is equal to 9, the radius of this circle is equal to 3. So let's take a look down here. We can parameterize that top surface then by r of xy equals the x and y components, just like normal, and then what the z curve was. So we're basically on the top here letting x and y be whatever they want to be, but the z component we're going to hold to be 9. And we're going to let the x and y run through x squared plus y squared is less than or equal to 9, and that's the disk that this is this projects as a shadow onto the xy plane. Okay. Next, we need to compute the tangent vectors in each direction. So we do the partial derivative of r with respect to x, and we get a 1 here, a 0 here, and a 0 here. So we just get I. The partial derivative of r with respect to y, same thing, we'll just get j, because we get a 0, a 1, and a 0. And then if we do the cross product of those two, we're doing I cross j, which we know is k. We don't even really have to write that down because that's something we've observed before. All right, so now that we have that, we can compute the surface integral. With everything you have here, and with the vector field that you have up here, this would be a good place to stop and actually try to compute that surface integral on your own. So I'll give you a second to pause the video and give this a try on your own. Okay, so to set up this integral, you're going to be looking at a double integral of f dot the ds, where the s here is the vector version of that, which we know translates into this. You just plug in the parameterization rxy and then put in the normal vector we choose. Now notice this normal vector is the one we want because as we set up here, we want it to be pointing up, and this one certainly is. It has a positive z component. So when we plug all this in, we get f of r of xy. That's putting in this curve right here, this surface, into this function up here. So you can see the only thing we really need to plug in is what z is, which is 9, which gives us this vector field here. So the y squared plus the 2xy plus the 18k dot the k here, that's the rx cross ry. So when you do a dot product, you multiply component-wise and add. So the y squared and the 2xy both multiply with a 0 because there's only a k component here, and you get 18 times 1. So you get 18 dA on this surface. Now this surface is a circle, basically, and so it's much easier to do this in polar coordinates, since everything we've done so far was done in Cartesian coordinates. We're just basically doing a regular double integral here, so we just change it to polar like normal. We get that theta will run from 0 to 2 pi, r will run from 0 to 3 because it's the circle of radius 3 centered at the origin, and then remember we get this r term here when we change those variables, so we got 18r. Computing that like normal, without too much trouble, you end up with 162 pi. So that's the surface integral of the top part. Now let's take a look at the surface integral of the bottom part. Now remember again, the normal vector here is going to be pointing down a little bit. So we need a parameterization for this. Well, we can do kind of the same thing we did before. We know the surface on the edge is z equals x squared plus y squared. So we could parameterize by x and y again and just let x be the first coordinate, y be the second coordinate, and z be the x squared plus y squared. And that's what we'll do down here for our parameterization. It's still x squared plus y squared is less than or equal to 9 because that's the domain basically of that surface. So we can compute now Rx by taking the derivative with respect to x, and we'd get a 1 and a 0 and a 2x, and that's what we get here. And in this, with respect to y, we'd get a 0, a 1, and a 2y, and that's what we have here. So computing a normal vector, we now just take this guy, the Rx, and cross the Ry, and we get the following. Rx cross Ry is this determinant here. You just plug everything in, compute the determinant, and you end up with this vector right here. But there's a bit of a problem. See if you can spot what the issue is, and this would be a good place to pause for a second to think about what the problem would be. All right, the issue is that this is pointing up, and we said that the normal vector we want is going to be pointing a little bit down, so it's going to have a negative k component. So this must be the other normal vector, not the one we want. So what we'll do, the normal vector we want is just the negative of this one then. So we'll negate it, and or which is the same as swapping these guys, so that's really Ry cross Rx. This is the downward normal, which is outward for the surface. So then we just go to the same stage. So we've got to compute the surface integral. And so this is a good spot to pause the video again and try to compute the surface integral of the second space. Of the second surface, I mean. So now we do the same thing we did before. We plug in the parameterization and dot product with this. That's a typo there. That should be Ry cross Rx. But anyway, what you end up getting when you put the Rxy in there, you're plugging Rxy into here. Again, the x and the y's don't change, but the z will become an x squared plus y squared for this one. So we come back down here, and you can see that's what I've plugged in. And then here's that normal vector that we're going to use. And so when you dot product these, you end up with 2xy squared plus 4xy squared minus 2x squared plus y squared. And that's what you get. And there should be a dA right on the outside here. I missed that too. So now we can swap this. Notice this becomes 6xy squared. Because the domain of this paraboloid is still basically the shadow of this circle, it's still better to do this in polar coordinates. So we'll swap from here to polar coordinates. So the xy squared, the 6xy squared, becomes 6r cubed, because there's an r in both the x and the y, and there's two y's here. So I get r cubed, and then the x will contribute the cosine theta, because x is equal to r cosine theta, and the y contributes a sine theta for each y that's there, because y equals r sine theta. So we end up with converting this part right here into polar to get 6r cubed cosine theta sine squared theta. And then this right here, x squared plus y squared, is just simply r squared, and so this turns in like that. And at that point, it's just a and don't forget, you got to toss in this extra r here because we switched to polar coordinates. From there, it is just a typical double integral. And so if you are careful and compute everything correctly, you will get that this integral equals negative 81 pi. So the integral of the first surface equals 162 pi. The integral of the second surface equals negative 81 pi. So the integral over the entire surface is just the sum of those two. So here's the surface integral. There's the integral over the first one and the integral over the second one. Boy, I kind of messed that up a little bit there. There should only be one dot here, and both of these should be double integrals. So sorry for that typo. And this will equal 81 pi, because it's the 162 pi minus the 81 pi comes out to 81 pi. So that's what the surface integral part is. So now the question is, what happens with the triple integral part? So we scroll down a little bit here. Now we got to look at the volume integral. So here's the region E that's just the interior of the surface we had up here. So if I scroll back up, now we're going to look at the interior of this surface. So that entire full ball, or not ball, bowl. Right, so everything on the inside of this. So you can see that the x and y still follow basically that circle, but that the z runs from x squared plus y squared all the way up to 9 in every case. And so that's what I'm describing here with the region E, is that x squared plus y squared is less than or equal to 9, so that's that circle, but that z runs from x squared plus y squared to 9. We're going to convert again to polar coordinates because it's going to end up working better. The next thing we need is the divergence of f. So if we pull up f again, take a look at that. That's this right here. To find the divergence, we need to take the derivative of this guy with respect to x, the derivative of this guy with respect to y, and the derivative of this one with respect to z, and add them all together. That's what we do down here. So you can see here that there's the derivative with respect to x of the first component, derivative with respect to y of the second component, and the derivative with respect to z of the third component. So here you get 0, here you get 2x, here you just get 2, leaving the divergence of f just 2x plus 2. So the triple integral of over e of the divergence of f dv equals, this should be a triple integral here as well, of 2x plus 2 dv. Now, at that point, we just plug in what we know about e. So we're going to use polar coordinates to describe this. So this will basically be r will run from 0 to 3, theta will run from 0 to 2 pi, and the z component, so really we're doing cylindrical coordinates, the z component will run from r squared to 9. And then we plug in the cylindrical coordinate formula, so x turns into r cosine theta, and then there should be parentheses on this right here, so 2r cosine theta plus 2 parentheses times the r here, so this parameter is going to distribute to both this one and that one, so again, kind of a lousy typo there. But I fixed it down here so you can see the r distributed to both pieces because that's coming from the change of variables. Alright, so we get our 2r squared cosine theta plus 2r, and then the z comes from here because we're integrating with respect to z. That's going to run from from r squared to 9. So plug in the 9 first for z, and then subtract plugging in the r squared. So I did that down here. If we plug in 9 for z, we get 18r squared cosine theta for the first term. Plug in 9 for z, you get 18r for the second term. Plug in 9 for z, and you get, subtract plugging in r squared. So plug in r squared for z, and you end up with this piece here, these pieces here to subtract, leaving a dr d theta. So the next thing is to integrate with respect to r, and so from here on it's just doing what you have typically done for integrals. So just be careful, try not to make any sign errors, and sure enough, if we keep going down here, we find out that this triple integral does in fact equal 81 pi. And that's exactly what the surface integral equaled, and so that shows that the divergence theorem held in this case. And so that's pretty much all we really wanted to see for the divergence theorem. So if you have enough now to do your homework, basically you're just going to be applying the divergence theorem to a bunch of different things. I will correct the typos in this document, and then when I post the video, I'll also post this document so you guys can take a look at this example and put it in your notes if you like. All right, thank you. I hope you guys have a good weekend. That's it for me. Please email me if you have any questions.